Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about wind tunnels part 2. So let's dive right into it. Now today we are specifically focusing on supersonic and hypersonic regime because there are many things that operate at the regime, so you have to understand those dynamics also. So we have bullets, we have jets, we have missiles, we have rockets, we have re-entry vehicle. All these puppies can easily cross Mach 2, Mach 3 or make even go to Mach 20. So we really need some fast boy. Now you have to understand this core aspect of it, that nothing, like even if you take SR-71, it's just not like, okay, I take off the runway, I do refueling, voila, I'm at Mach 3. It's not a photon. It takes time to get up to speed. That means it crosses some regimes, meaning it couldn't go from subsonic to supersonic. That's a very naughty regime. And in those sort of scenario, you have to have a tunnel that simulates that, meaning it cannot be like, I turn on the tunnel is like Mach 3. No, it has to slowly go through that. Ideally, you should be able to control that way. So that means if you're designing a tunnel, you cannot just be like Mach speed. You have to like, let's ramp it up. All that thing, that does matter. And whenever you are talking about supersonic speed, you do have to understand shock waves. These things become destructive, not only destructive to your models. If your model is not built properly, it will shatter. And be mindful, at this point in time, you're gonna fling things at Mach 2. It can punch through walls at that point in time. So it's a very serious thing that you have to understand shock waves. And not to mention, shock wave cannot, even if your model is like, I'm God, I can withstand it, it could cause damage other things. You have to take that into account, so to say. Shockwaves are serious things. It's not a laughing matter, especially if you have acrylic windows. You have to be very mindful of that. Bad shockwave, boom. So you have to understand it. And because of the high speed regime, you also need high speed data logging. Even if you have a continuous tunnel, let's say the tunnel that can just keep operating for 4 or 5 hours, you have to understand, if something goes bad, it goes bad spectacularly quickly. Meaning inside a second, you could literally go from every airflow is completely stable, something bad happened, poof, and it could have all happened inside 1/100th of a second. So you need very high speed data logging. You cannot operate these sort of machines in a regime where it's like, oh, I'm taking 1 hertz sampling. No. You gotta go into kilohertz or even megahertz. You really need super duper hyper high speed data collection. Because again, there is a tiny model that somebody's trying of SR-71, everything is fine, everything, it starts vibrating and so you need to know what happened. So in those sort of scenarios, you have to, everything about this is high speed. So what was the physics? Well, physics is, if you really want to do this, you have to understand one thing flat out of the gate. These things are energy intensive, meaning if you ever even dream of building a supersonic tunnel, you're looking at 100 plus megawatt or maybe hundreds of megawatt of power consumption. So these boys are hungry. And how do we achieve that speed? Well, we achieve it by same way we achieve speed in a rocket or nozzle. Convergent divergent nozzle. Now this nozzle, you can go into mathematics. I like to think about them in very simple terms. They are like transformer. So same way a transformer can take a very high amp low voltage, make that puppy into super high voltage and super low amps. You can do the same thing with flow. Now be mindful, flow is compressible, so dynamics are a bit different. It's not like water. If you compress it, it will keep going faster and faster unless you get, water jet cutter. That's not going to happen with air because air heats up, so it's compressible. So you have to figure that part out. So what does that mean? That simply means you put GG amounts of pressure. Pressure creates a choke flow, meaning air tries to go fast, but it cannot go fast. Basically, it will reach Mach 1 at throat. The moment that happens, you reach what we call choked flow. We always want this. We want the choke flow. Now, choke flow means majority of your energy is not converting into anything like in terms of velocity. So basically, you're reaching as fast as you can, Mach 1. Now, here's the interesting part. If you let it expand, it's going to act like a converter. Basically, it's going to convert heat and pressure into super high speed. Basically, you just converted high voltage into high amps. So you have basically convergent divergent order in the inlet side. Now, if you directly have this and you send it through a testing area, will it work? Yes, there are many open supersonic tunnel, very small models. Generally, they have like a giant vacuum pump that like very small tunnel for short duration. It can be done. Like all you will get is this, like nozzle, testing section, done. However, if you want to have even more control, more speed, at that point in time, you have to put a second diffuser section, which is basically this nozzle in reverse. Basically, you want air to relax, to phase out from basically super high speed to low speed. The reason for this is basically if you do not do this, the inlet pressure requirement goes exponentially high. You want inlet pressure to be as low as possible so you can sustain that. So if you have to put, let's say, 50 bars of pressure here, that's acceptable. If you do not have this, you may end up needing to put, let's say, 500 bars here. At that point in time, that's very unmanageable, so to say. So we also put a second layer. Now these things are designed in such a way that it uses the shock, the basically normal boundary, to do this in reverse. Basically it's like, okay, let's let the air calm down, go from basically high flow to high pressure. So test section, this section basically should not have any shock waves. So shock wave should be always be in the diffuser, it should not be here. And shock wave will always be formed whenever you are changing velocity and all that jazz. So test section should not have normal shocks, and air temperature needs monitoring, because what you are doing here, basically taking high pressure and high temperature and expanding that, you are expanding that, meaning it will cool down, meaning you can literally, if you try to do very extreme and you're like, oh, I'm going to send very high pressure air and I want hypersonic speed on the other end, you're not going to get anything. You're going to get vacuum on the other end. It's like, how the heck you got vacuum? Well, temperature dropped so much that air condensed, meaning you're going to have liquid nitrogen and carbon dioxide and basically liquid oxygen at the other end. So the temperature have to be managed. So you may, in some designs, you may have a preheater that heats up the air depending on the temperature requirement, depending on the speed. There will be a calculation that will show you. It's like, hey, I think you need to make sure the air is at least 300 degrees Celsius hot. If it's not during that expansion period, it's like cool down too much. So these are the physics. Then we come to the closed loop. Now closed loop, you have to understand, same thing, you have subsonic high pressure flow and you convert that puppy into basically cool supersonic flow. And it's actually kind of desirable because in high altitudes where we actually have supersonic vehicles and missiles and all that jazz, they actually experience cool air. So it's kind of, ironically, it does make sense. And you be mindful, like at a very high altitude, it's kind of cool air. So you get that. Now at that point in time, the pressure required is so high that fan no longer work. You need these puppies. Basically, jet engine had a baby with a giant. This is what they are. Huge puppies. These are axial compressors and they are giant. I mean, they can easily consume hundreds of megawatt, and not to mention the RPM has to go down because again, the size are huge. Like the building size, they cannot spin at like jet engine size where like 100,000 RPM or like 50,000 RPM or even 10,000. They have to be like under 1,000. But they do consume power and they compress hell lot of air. So you have basically fan, air gets there. Of course, you may have a heating section here, and then you basically convergent divergent nozzle. Voila, you get your high speed. You let it diverge out, and then you recirculate it. Now, because this is a closed loop system, it also allows you to do something interesting. Because of the inherent limit that you cannot make it air too hot. Again, it will become plasma if you heat it up too much. And not to mention, it will also add too much cost. What if you change the gas mixture? Because again, liquid nitrogen has a temperature. What if you use something different? For example, helium. You can do that, and people do that in some scenarios where they're like, I really need hyper high speed, meaning if you want to cross, generally it said Mach 4 to 6 or 8 regime, you may need to change air to helium or argon depending on up to your requirement. Generally people change it. Now, is that absolutely accurate recreation of what's going to happen at high altitudes? No. Is it useful? Yes. So people do it. Because again, shock geometry is the same. So, and be mindful, you can calculate for pressure and compensate for it. You'll get exactly same results. The only alternative at that point in time is might as well send a high altitude testing. That would be the final stage. You will refine the design using helium, and then you're going to test it using rockets. So this is a closed loop architecture. Now closed loop does go fast, but does not go like, Mach 20 plus kind of fast. At that point, you need blow down systems. Now blow down system is basically hypersonic regime, meaning anything that crosses Mach 7, basically if it starts at Mach 7 or something like that, hypersonic regime. Now they have basically very, very high, but no compressor at that point in time works. So you need something like a high pressure reservoir, meaning reservoir can dump. Now, if you directly try to dump it, it's gonna give hypersonic for a few pulse and voila, gone. So you also need a big vacuum tank, meaning you have a positive pressure and a negative pressure, then only hypersonic flow can be sustained for more than a shock wave, because shock wave will be created and then it's like everything is normal. So you need that pulse to be hypersonic for long duration. You need a vacuum negative space also, and that's why like these have giant balls. Like you can literally go to a hypersonic test center. The bigger the size of the balls, the number of the balls, you can figure out how powerful this puppy is. It is directly attached to the balls. So that's the only thing, and it only works for a few seconds. You do not expect it to like, I'm gonna turn on and do this. Supersonic you can do, hypersonic unlikely. So at that point in time, you just get a pulse, and then you will change the geometry, meaning in this is a Indian DRDO design. You can see there are multiple chest chamber. They will open that rail, they will slide a different chamber. Again, one could be for Mach 2, one could be Mach 3, one could be basically Mach 1.5 or maybe even Mach 4 if they need to. So you change the geometry to achieve the speed you desire, and you need super speed sensors. Again, it's inherently pulse. It's not even like supersonic where you have time to, okay, things are happening, I'm calculating. It's not. instant. So you really need super high speed sensors here. And custom gas mix can be used again. It's kind of easy because you have a pressurized area, so you can pressurize with some other gas like argon mix, helium mix, things of that nature. These are blow down, and this is like China's system that they have built very recently. Now that's just the core aspect of it. There are some extra things also. Now if you have money, and if you have really lot of money, then you can go into this puppy, which we call active geometry manipulation. At that point in time, especially in supersonic tunnels, if you want something like ICBM re-entry testing, ICBMs took money to develop. Like we kind of forget like how fast ICBMs are. Like really, really fast. They are so fast, they will take over basically hypersonic system multiple times. And not to mention, somehow entire world thinks that basically ICBMs can be intercepted. Yes, in principle, but they are so cheap you can launch hundreds of them. So hypersonics are like the final weapon, like, and to children. Like ICBMs are the god tier killing weapon. It's like, bro, I've been here. Like hypersonic, no, I'm here, bro. I'm on a whole different. And this is how we developed it. Especially if you talk about here and you say re-entry, retargetable vehicles. That's how it was developed. Because again, you need to have a study material where it's like going from orbital speed to sonic speeds, and you need to figure out like how the heck it handles that regime. Because if you do not handle it, it's gonna tumble by your controls or guidance. So you need to figure that part out. And for that, you need some wind tunnel that has oomph, so you can sustain the power, and it has a geometry that allows you to scale that system, meaning go from Mach 1, Mach 2, Mach 3, Mach 4, Mach 5, Mach 6, and ideally at the same speed as you will experience in real life. So these things are very, very expensive. Like let your bank balance go, that kind of experience. And I'm talking about country level. No private company can even dream of doing this. So very, very serious amount of expenditure. That's just the active part, ICBM development part. Then what if you want to develop supersonic ICBM delivery vehicles? At that point in time, you need supersonic and you need it continuously. At that point in time, you have to deal with what we call boundary layer, meaning no matter how fast your flow is, no matter what you do, like you can go Mach 20 or Mach 500, does not matter. You're always gonna have a layer of air that is acting like an insulator. Now it's also insulating against speed, meaning if you make a tunnel that is, let's say, 10 square meter, and you're like, how much of an area I'm getting that is laminar flow? The answer would be very low, because again, boundary layer will create a basically blanket around. So you have to deplete this blanket layer. To deplete that, especially on continuous system, you will have holes around the wall. Basically, these are exactly like how you have golf ball dimples. They are in reverse. Now be mindful, they are not venting to the atmosphere. That will ruin your energy budget quickly. So they again vent from outside, but again it keeps the boundary layer in check. So rather than boundary layer wasting, let's say, 20% of your surface area, it only wastes 10% of your surface area. So you also have to do this. Another aspect is the physical practicality, that you are making a model. No matter how good you are, is that you can only put few sensors there. You cannot put 10,000 sensors. So what people do many times is they use pressure sensitive paint. Now the benefit of that is that gives you a very granular picture. And of course you will have sensors. So sensor allows you to calibrate the data. So you're gonna put sensor here, 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 and then you're gonna coat everything in pressure sensitive paint. Based on that, you can get both of them can help each other collaborate the data, and you're gonna have a very fine picture. It's like what happened to the plane, what happened to the airframe, all that data. But be mindful, it does take a lot of prep work. Why? These things are dealing with some serious amount of stress. Even though they look like a toy, they're dealing with some high speed things, meaning they can easily survive Mach 2 easily. What does that mean? That simply means if any chunk breaks off, it's gonna travel at sniper bullet speed, meaning these puppies are fast and dangerous. So it has to be taken care of like very seriously. You have to figure out every nut and bolts. Accidents have happened and they would have damaged very, very expensive tunnels, and people have figured out how to make sure that that does not happen. Like these are things that require very serious safety, not only for the models but also for the equipment itself. And only few countries have like supersonic and hypersonic kind of things. For example, United States, Russia, India, China. India is third. We were the third to get it, and China just recently announced it. So these are some expensive puppies, especially this one. That's like I really have some deep pocket. That's like mine's really bigger than yours. So this was my presentation on Wind Tunnel 2. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike. Press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.